This might be the most shocking feature in all of Antarctica.
A glacier in Antarctica appears to bleed. The water is red, metallic, and real. For decades, people thought they understood it. Then scientists traced the color backward through ice, chemistry, and time, and found a hidden world that should not be alive. A waterfall that should not exist. Picture the McMurdo dry valleys, a place so cold and dry it is often compared to Mars. The wind scours the rock, the air bites. Most days, nothing here looks capable of movement, let alone water. And then you see it, a streak of deep red spilling from the face of Taylor Glacier into a frozen lake like rust poured onto snow. This feature has a name that sounds like a myth, but behaves like a physical fact. Blood falls. It does not run like a river. It surges in bursts, staining the ice, fading, then returning again, as if something under pressure is periodically exhaling. The first instinct is to ask the obvious question. In temperatures that can plunge toward 48 degrees C, how is anything flowing at all? The second question is worse. What is the glacier releasing, and why is it the color our brains instantly label as danger? The wrong answer that lasted nearly a century. When geologist Griffith Taylor documented the phenomenon in 1911, he did what scientists often do in the field. He reached for the simplest explanation that fit the surface evidence. Red stains on snow and ice can be biological. Snow algae are real, and in many cold environments, they tint ice pink or crimson. The idea sounded reasonable enough that it became the story people repeated for decades. But blood falls was never a biological paint spill on the surface. In the late 1990s and early 2000s, geochemist W. Barry Lyons and colleagues tested the outflow directly. Using full geochemical analysis, the results were blunt. The water contained extraordinarily high concentrations of iron, far beyond anything algae could account for, and it contained no chlorophyll. The redness was not life on the ice, it was chemistry in the air. Once that clicks, the waterfall becomes even more unsettling because the mechanism is easy to visualize. The brine emerges clear beneath the glacier. The moment it meets oxygen, dissolved iron oxidizes. It rusts in real time, turning the water that visceral, mineral red. The glacier is not bleeding, it is breathing out an ancient brine that turns to rust on contact with the modern world. That solved the color. It did not solve the source. Where would an iron-rich liquid reservoir come from under hundreds of meters of ice? Listening through 470 meters of ice. To answer that, scientists had to see without seeing. The tool was ground-penetrating radar, which sends signals down into the ice and measures the echoes that return. Ice and salty liquid reflect those signals differently, so brine can show up like a bright signature against a darker background. In 2004, glaciologist Alan Hubbard and his team hauled radar equipment across the surface of Taylor Glacier. They found the ice was nearly 470 meters thick, which meant anything liquid had to be insulated, pressurized, or both. Still, the early surveys could not fully resolve the shape of what was beneath them. Over a decade later, Jessica Bagley and her team returned with more precise radar. They moved slowly, methodically, building a subsurface picture from thousands of returning pulses, the way a bat maps a cave by echoes. And the more they listened, the clearer the structure became. What emerged was not a small trapped pocket. It was an extended network of brine channels feeding an underground reservoir that sprawled hundreds of meters across and stretched kilometers inland. The hidden system was enormous, on the scale of multiple football fields lined up end to end. So the glacier was not leaking a stain, it was venting a plumbing system. How water stays liquid at 7 degrees C. Now the story turns from mystery to physics. Liquid water should not persist beneath a glacier in that environment, unless the water is not normal water at all. The brine under Taylor Glacier is extraordinarily salty, roughly 80 parts per thousand compared to about 35 parts per thousand for typical seawater. That salinity drags the freezing point down. Over millions of years, advancing ice forced liquid water away and concentrated the salts that remained. Researchers measured the brine flowing at about 70 degrees C, a temperature that would lock fresh water into ice almost instantly. Here, it stays liquid because it has been chemically rewritten by time and confinement. Pressure adds another push. Beneath the glacier, the brine sits under roughly 2.6 megapascals, the weight equivalent of dozens of cars pressing down on each square meter. Pressure alone is not enough to save liquid water here, but combined with extreme salinity, it helps keep the system just on the liquid side of the line. Then comes the counterintuitive part. As the outer edges of the brine slowly freeze, the phase change releases heat into the remaining liquid. Glaciologist Aaron Pettit and others have emphasized that this freezing-driven heat can be enough to keep surrounding brine persistently liquid, making Taylor Glacier the coldest known glacier with flowing water. So the glacier does not defy cold, it exploits chemistry, pressure, and the physics of freezing itself. A hidden ecosystem with no oxygen. Even after you accept that liquid can exist, Blood Falls still has another surprise waiting in the brine. The outflow is not continuous. It arrives in irregular bursts, and before it ever reaches air, it is sealed away from light. That isolation makes it a perfect test of a question people rarely ask out loud. What if an ecosystem never sees the sun? In 2003 and 2004, microbiologist Jill McCookie and colleagues showed that the brine was not sterile. Using direct sampling and DNA sequencing, they found microbial communities living beneath the glacier, metabolizing and reproducing in conditions that read like a checklist of impossibilities. Darkness, extreme cold, extreme salinity, and water saturated with dissolved iron. Some of the organisms identified belong to sulfate-reducing groups, including Desulfosporosinus. They are strict anaerobes, meaning oxygen is lethal to them. That detail changes the emotional tone of the story. The red color that fascinated explorers is produced when the brine meets oxygen at the surface. But oxygen is exactly what the resident life below cannot tolerate. These microbes survive by extracting energy from sulfate in surrounding minerals, a low-yield strategy compared to oxygen-based metabolism. The brine is not just a strange liquid, it is a living system running on a budget, enduring for geological spans with minimal energy because it has no alternative. The question stops being, what makes the glacier red, and becomes, what else can life learn to live without? A time capsule that mimics ancient Earth. Then the timeline expands. Chemical signatures indicate this brine was once seawater, trapped when Taylor Glacier advanced and sealed off a fjord during the late Miocene. It has likely been isolated for roughly 5 million years. 5 million years without sunlight, without air exchange, without contact with the surface world. That matters because isolation does not just preserve water, it preserves conditions. The brine remains oxygen-free, which makes it an analog for environments on Earth before oxygen reshaped ecosystems. The Scripps comparison to the Great Oxidation Event works as a narrative lens, as long as we hear it correctly. The brine is not a 2 billion-year-old relic, but it mirrors the oxygen-poor chemistry that dominated long before oxygen became the planet's atmospheric signature. In that sense, Blood Falls is a letter from deep time, written in iron chemistry and delivered through ice. It forces humility because it shows how quickly human explanation can harden into tradition and how long the real story can wait underneath, unchanged. Why Blood Falls points to Europa. Once you accept that life can persist in cold, salty, oxygen-free darkness, the leap to other worlds stops sounding like science fiction and starts sounding like a research program. Beneath the cracked ice shell of Jupiter's moon Europa, evidence points to a salty ocean sealed away from sunlight. The parallels are not perfect, but they are strong enough to make Blood Falls a serious analog site for studying icy world chemistry. Enceladus raises the stakes even more. The Cassini mission detected jets of water erupting from its south pole, implying an ocean with hydrothermal activity. On Earth, hydrothermal systems are deeply tied to theories about life's early origins. Blood Falls, in comparison, becomes a local training ground for the mindset and methods we will need to interpret alien oceans. NASA formally designated Blood Falls as an analog site for sulfur and iron chemistry on icy worlds in 2016. That designation is not poetic branding. It is a statement that the chemistry that stains Taylor Glacier may resemble the chemistry we will have to recognize if we ever sample brines beyond Earth. And this is where the timeline becomes specific. Europa Clipper launched on October 14, 2024, tasked with evaluating Europa's habitability by probing the ice and analyzing surface material. It is not a life detection mission, but it uses principles that rhyme with what revealed blood falls in the first place: remote sensing, radar, and careful inference. The twist is that blood falls changes what habitable even means. It is not about warmth. It is about chemistry, gradients, and persistence. Why this matters for Antarctica's future. There is another reason this story matters, and it is closer to home than Europa. Blood Falls is the only known surface discharge of subglacial brine in all of Antarctica, but evidence suggests brine networks may extend beyond Taylor Glacier, threaded through bedrock in the region. If that is true, we are not looking at a bizarre exception. We are looking at one visible window into a hidden category of systems. Even now, our maps of Earth still have blind spots. As of June 2025, the Seabed 2030 project reported that only 27.3% of the global seafloor had been mapped to modern standards. If we still struggle to chart the ocean floor, it is no surprise that what lies beneath kilometers of Antarctic ice can stay hidden for decades. For more than a century, explorers could see the red stain and still miss the world responsible for it. The revelation did not come from traveling farther, but from learning how to listen, how to sample carefully, and how to doubt a convenient answer. Somewhere under Antarctic ice, and possibly under the ice of distant moons, chemistry may be sustaining life in the dark right now. Blood Falls is a reminder that discovery is not rare because reality hides, but because understanding takes time.